Okay, so we have seen how when a function is analytic, there's a Taylor series of expansion available, and even if a function is non-analytic about a point, we often have a Laurent series available for it. So in this lecture, we will look closely at the idea of singularities which are isolated. Right? So there are different types of isolated singularities possible, and so this will come in handy when we discuss the next topic, namely the residue theorem. Right? So in that context, it's useful to classify singularities and understand what kinds of singularities appear, and so that's the topic for this lecture. Okay, so we have encountered lots of functions which have non-analyticities but restricted to a finite number of points. Right? So a simple example is 1 over z. Right? So if you have a function like 1 over z, then it's well behaved, it's analytic everywhere except at the origin. Right? So similarly, there are other functions which we have seen where such non-analyticities are restricted to a finite number of isolated points. Right, so let's define isolated singularities, an isolated singularity a little more precisely. So we call a point z0, a singular point if it is non-analytic, but it's analytic at some point in every neighborhood around z0. Right, so this is about a singular point. So you'll always be able to find some analyticity in the neighborhood, then it's a singular point. But if it's also called an isolated singular point if it's analytic everywhere in its neighborhood, right? So if there is a deleted neighborhood, right, that's a technical term. So deleted neighborhood simply means some region 0 less than mod z1 z0 less than epsilon 1. You're able to find some radius and a circle of radius epsilon 1, and every point inside this region is analytic except this point z0. So that's what is meant by this deleted neighborhood, throughout which f of z is analytic. Then you say it's isolated, right? But in general, a singular point need not be isolated, right? So for example, if you have something like log z, right? So the function log z it has a singularity at the origin, but it's but also along an axis. So it's not even defined along the negative x-axis. If you take that to be your branch cut, right? So you could, of course, by convention, choose a different branch or a different branch cut. But in any neighborhood, you will find other singularities as well, right? In general, you can have singularities which are not isolated, but it would be isolated if you have, that's the only singularity. I mean, you may have another singularity sitting at a finite distance away, but all points in between these two singularities have to be analytic, right? So this whole region around this point, if it is analytic except that point, then it's called an isolated singularity. Now, since this function is analytic in this annular region, epsilon 2, you can always come up with some epsilon 2 less than mod z minus z naught less than epsilon. We can epsilon 1, we can write down a Laurent expansion, and that is valid in this region. So you have some expansion which has all these coefficients ans and bns. You write down summation over n an z minus z naught the whole power n, positive powers, and then summation over bn. These are also positive indices, but basically the powers are in the denominator. So you can think of this as bn divided by z minus z naught the whole power n, and n goes from 1 to infinity. So in general, right? So but since epsilon 2 can be made arbitrarily small, basically you say that this Laurent expansion is valid everywhere in the region 0 less than mod z minus z naught less than epsilon 1. So this radius epsilon 1 is often as large as the distance to the nearest singularity. From a given singularity, there's another point of non-analyticities somewhere else, which is, so you just consider the nearest of these singularities, and that would be this epsilon 1, but it could be a smaller one as well. So it does not matter how large or small this epsilon 1 is. The key point is that there is a whole circular region which encloses this point, and in that entire region it's analytic, and therefore you are able to write down a Laurent expansion of this kind. So now if you are able to write down a Laurent expansion of this kind, so the nature of the singularity is determined by these coefficients Bn basically. So An, that's the regular part, which contains, information about the regular part is contained in these coefficients An, but Bn carry information about the nature of this singularity. And depending upon what kind of Bn, the set of coefficients Bn you have, there are three different cases, and it's useful to look at these three cases in some detail. Now, the first of these cases is something we have already encountered, which is when if all these Bn are 0, right? So then you basically have a scenario where only the An exists, and so it's like a Taylor series expansion, except that there is a small subtlety involved here, and which is that the function may not be defined at this point. So that you still have a singularity, but there is it's what is called a removable singularity. So the reason is that the limit of this function f of z as z tends to z naught exists because it is going to be a naught, and therefore if the function is not already defined to be a naught at that point, you just simply say that we call this function, we equate this function to f of z as long as z is not equal to z naught, but we will just redefine it to be a naught at the point z equal to z naught. And if you do this, then you get a well-defined Taylor series expansion. I mean, the Taylor series expansion is already there, and this function is an analytic function. It's analytic everywhere. So this is why it's called a removable singularity. This is of a sort of a trivial kind in some sense, right? We have already encountered this kind of a removable singularity. A simple example is that of the function sine z over z, right? It's not defined at the origin because of the 0 by 0 form. So it has a singularity at the origin, but you can just simply redefine this function to take the value of the limit at that point, which you can easily extract by simply writing down the Taylor series expansion for sine of z, and then you see that the leading order is z, which will cancel with the denominator, and so basically the limit of sine of z divided by z is going to be 1 as z tends to 0, and this is the same regardless of which direction you approach it from. So it's continuous, and in fact this is analytic everywhere, right? So you have a well-defined Taylor series at all points, and so this is an entire function. Now let's look at case 2, when you have some of these coefficients Bn's are non-vanishing, but not all of them. So a finite number of Bn's are non-vanishing. Then you'll basically be able to find some largest of these coefficients, largest index coefficient. So there exists an m such that Bm is not equal to 0, right? So you don't have to have Bm non-zero, not equal to 0 all the way up to m, right? You find some particular m whose Bm is not equal to 0, but you must have the condition that Bn is equal to 0 for all n greater than m, right? All higher order coefficients for sure are 0, lower order coefficients, some of them may exist, some of them may not exist. Then you have a scenario where you can simply multiply such a function at this point by this power z minus z naught the whole power m, and then you're guaranteed that this new function g of z is going to have a removable singularity at this point z equal to 0, right? So, and then it becomes possible to redefine this function g, as z minus z naught the whole power m times f of z, if z is not equal to z naught, and it is equal to bm if z equal to z naught, right? So bm is the coefficient which is critical in this, for as far as this new function is concerned, right? It's not a naught but bm, right? So bm will play the same role as a naught played in the previous discussion, and then it becomes analytic at z naught, therefore analytic in some region around it in the neighborhood. And so in this case we say that the function f of z has a pole of order m at z naught. A pole of order 1 is called a simple pole, right? We have encountered simple poles, and so in the Laurent expansion of the original function, so this is a very important definition, if you wish, at this point, is that of the residue, right? So among all these coefficients, when you have a Laurent expansion of this kind about an isolated singularity, all these coefficients are important to some extent, but there is one coefficient which is of great importance, and that is this coefficient b1. And this coefficient b1 will have the corresponds to the term 1 over z minus z naught, right? So b1 divided by z minus z naught is of paramount importance, and so this coefficient has a name, and it's called the residue, right? So the residue of a function f of z is simply defined as the coefficient b1 in the Laurent expansion of this function when it is expanded about of an isolated singularity. Now, this is true in general, right? It does not have to be a pole. It's an isolated singularity, but when you have a pole of order m, there is a way to compute this residue with some ease. So let's look at an example. So if you have this function cos z of z, instead of sin z of z, I can think of cos z of z. Now it is a real singularity. It's not of a trivial kind. It's a genuine singularity, and it does not have, it's not defined at the origin, and there is no simple way to redefine this function at that point and get rid of the singularity. It exists. So if we expand the cosine function, we have this series expansion we already wrote down, 1 minus z squared over 2 factorial plus z to the power 4 over 4 factorial minus z to the 5 by 5 factorial, so on. All of this stuff divided by z, and then you can pull out this 1 over z outside, and then you write down this as 1 over z minus this summation n equal to 1 to infinity minus 1 to the n z to the 2n minus 1 divided by 2n factorial, right? So let's check if we got this sign right. So I have a 1, so it is just simply minus 1 to the n. So if I put n equal to 1, and then I have z to the 2n minus 1 divided by 2n factorial. Let's look at the first term. So if I put n equal to 1, so it's a minus 1. So then you have a z divided by 2 factorial, which is maybe I have overcorrected for this. So this should be just 1 over z plus 1 over z plus. So then if I put n equal to 2, then this is 3 z cube divided by 4 factorial, which is good. And then if I also n equal to 2, it comes with the positive sign. Yes, so this is correct. And so this function has so this is the expansion for this function, and it has a genuine pole, and it turns out to be a simple pole, because you see that it's just 1 over z, and all of this is the regular part, and the coefficient corresponding to 1 over z is just 1, and that's the residue for this. It's a very simple, it's straightforward to evaluate the residue. But we'll come back to the residues a little bit later. Let's look at the third case, and that's when you have all of these bn's are non-vanishing. So then you have this isolated singularity is what is known as an essential singularity. So there is no way that you can multiply by some factor of some power of z minus z naught, and you cannot cure this singularity. I mean, it's going to remain no matter with what power of z minus z naught you multiply at this point. This is an essential singularity at this point. And so the standard example for an essential singularity is this function e to the 1 over z, right? So we have already looked at this kind of an example. So there is a singularity at the origin, and it has this expansion 1 over n factorial z to the n, and so no matter with what power of z you multiply this, there is going to be a singularity, because all powers of 1 over z are there in this expansion. So there is an essential singularity sitting at the origin. So whenever you have an essential singularity, there are some, it has certain weird special properties around this essential singularity, so that the function tends to take basically any value you wish in its neighborhood, right? So there are interesting properties of this weird kind of singularity, which is our for very drastic kind. But in general, we are more interested in poles, and so residues of poles and these kinds of things we will discuss in great detail. And so that's where the power of the residue theorem, which also is coming ahead. Most of it is going to be actually connected to poles, right? That's where our discussions are going to center around. However, we should be aware that there are other kinds of singularities. So one of them is of a trivial kind, the removable singularity, which was case 1. So this is actually case 3. So there is case 2 and case 3. Case 2 is the standard kind. Case 3 is a very special, weird kind, which is also not very frequently encountered except in these kinds of special cases. And then there is case 1, which is of a trivial kind. So that's the 3 kinds of isolated singularities which we have looked at in this lecture. Thank you.